Arabic translation of sustainability, which means istidama. Istidama that we need to have our source of energy as long as possible. So, most of the world now depend or rely on energy to do like engines, motors, all, or electricity even to do our work, as we said. But electricity even itself come from fossil fuel, car engine by fossil fuel, like what we have all. So to say we work on extending the lifetime of our resources of energy, especially conventional resources like the oil, coal, natural gas, we need to raise the efficiency uh, of our conversion systems, our energy conversion systems, raising the efficiency in all stages actually of this energy conversion chain, starting from the first step, which is generation of the energy, while we are burning the fuel in gas power plants or in steam power plant, raising, especially this is central or mega size of energy conversion. So improving the efficiency by 1% actually save a lot of fuel, tons of fuels. Also, in the electric transportation, when we transport it by efficient transformer, efficient power transmission lines, this also save some energy and at the end save fuel. Also, in the user side, I think you have a course on demand side management. You need to also improve the efficiency in your AC, in your refrigerator, and your washing machines. So you are going to save also some energy at the end side, which will trace back to the generation. You will at the end raise fuel. So raising fuel mean we are going to burn less fuel for the same power produced, which mean save more money, extend the life of the fuel resource, and also reduce the CO2 and other emissions, and improve the footprint of our plant on the environment. Also, reducing this or raising the efficiency, would it be also economic or raising the profit of the electric company? This is need discussion. We cannot say, of course, raising the efficiency will reduce the fuel and this will reduce the running cost. But the decision to do this change or technology, introducing new technology to raise the efficiency, it has a capital cost or initial cost. We had to carry out life cost analysis of what we are going to modify or the new plant and see if this is increasing the profit to the existing one or not. So, but usually yes, but it is not direct answer. Improving the efficiency, reduce the fuel, increase the profit is not always yes. You have to do your analysis. The analysis is two parts. Part is thermodynamic, and this is what we were focused on module 1 and module 2 so far. And the economic also started on module 1, and we'll try to apply more here in this module. Um, so to decide what we are going to do, we have to make the question clear. What we need to do in our plan to reduce the amount of fuel burned for the same required power from our company. Um, then what are the technologies that exist that we can use it in different way? Like for example, we have the gas turbine. What we can do? Can we do reheat? Can we do regeneration? How much it will cost? Also steam cycle. Can we do reheat? Can we do regeneration? Can we do combination of them? Or how can we merge the solution to the current problem with solution to a different problem in order to create a new solution? Like for example, we have combined cycle. We integrated gas turbine with a steam turbine to generate electricity from both turbines. Like the exhaust will have problem to solve a combined cycle cogeneration, to do more than one, to take electric power and take some steam for desalination, for example. So we have heat and power. or we take the heat or the steam for industrial process like heating a chemical or heating a clothes in a clothes factory. Trigeneration, we can have a power plant that or a system that can generate electric power. It can be also running cooling or heating system, cooling in hot places and heating in cold places. And desalination, we have multi-degeneration. Always now the trend is to have from one source of energy, which mainly here we are talking about conventional fossil fuels, but also it apply for solar energy as a source. We can have one source of energy and we can make use different application depend on the temperature level we have. We can have power generation we are at high temperature level from the cycle. Then the exhaust of the power generation system can run another power generation, like in the combined cycle. We have the gas turbine, then the exhaust of the gas turbine used in the boiler to boil steam and so on. And the exhaust of the boiler before going to the chimney, it can run absorption cooling system or absorption. Also, we can have it for desalination. If we have a brackish water or even seawater, we can help to desalinate the water and some stage. So there are some work from worldwide. Also, Dr. Hunter has some, and his group has some work in this type of multi-generation. Also, there are patents. Dr. Hunter, myself, and some student, we have patents in this and trigenerate. We might have, I have also some work on combined cycle integrated to solar or independent. So these new ideas are coming. People are working together. Who did something? Someone else come and take this idea and apply it or use it in another new system. So we have here a quick example that we have a combined cycle similar to the one we gave in the gas turbine. It's a simple gas turbine. We get its efficiency and we have added to it another simple steam cycle. So the exhaust of the gas turbine give the or run the boiler of the steam cycle. So it's saying here consider an ideal combined cycle. Yani reversibility is not counted. I mean the expansion is isentropic. Also compression is isentropic and no pressure drop in the pipes due to friction. So the gas turbine has a pressure ratio of 7:1 in which air entered the compressor at 295. This is the inlet to the compressor, and then heated in the combustion chamber and enters the turbine at 1200 Kelvin and exits the heat exchanger at 400 Kelvin. This is the gas exit from the heat exchanger for the combined cycle where it heat the water. And the steam cycle, steam is compressed to 8 megapascal by the single pump we have, heated to 400 in the boiler, 400 degree in the heat exchanger, and then condense it at the pressure of 10 kilopascal in the condenser. He wants the theoretical efficiency of the cycle and compared to the efficiency of the two separate cycles, the steam cycle alone and the gas turbine cycle alone. Of course, the steam cycle alone, we solve it maybe with Dr. Hunter at the beginning of the steam cycle. And also gas turbine, you solve it the simple one with me last time. So I will not go in details. This just remind you of the cycle. The top one is the gas turbine cycle, as we have air come from the compressor, as he said, at 295, go out enters the at 6 here and go to the combustion chamber, come at 7 at 1200 Kelvin. Then the exhaust, he didn't give to us a temperature. We can get it from isentropic relation between 8 and 7. But 9 he gave us as 400 Kelvin, while the steam come here from the pump here at 10 kilopascal at 1. So temperature is from saturated table, you can get it about 45 degree or something. Then we add the work of the pump, we can get enthalpy at 2, which is enthalpy at 1, HF at 10 kilopascal, plus V delta B, we can get H2. But they give us the outlet here, 3, at state 3 of the steam is 400 centigrade. Then through the turbine, after the turbine, we expand up to 10. So we can actually solve this cycle what we need, if we drew the TS diagram of the steam cycle, 1 to 2 in the pump, 2 to 3 in the boiler or the heat exchanger, 3 to 4 is in the turbine, 4 to 1 in the condenser. Actually, here also we can get state 5 inlet to the compressor of the gas turbine, 6 outlet of the compressor. Then 7 is he gave us the pressure is 7 atmospheric pressure, and temperature is 1200 Kelvin. So we know the property at 7. With isentropic expansion, we can get the property at 8. So he gave us 5 and 7, and 6 will be getting through the isentropic relation of 5. And 8 is from the isentropic relation from 7, as we solved the example of simple gas turbine cycle. And then we get, as I said, properties using for steam, saturated table of steam, and superheated table. Saturated table, we get H1, which is HF at 10 kilopascal, and 2, we get H1 plus V delta B. This is state 1 and 2. You'd see the difference is about 8 kilojoule per kilogram, which is the work of the pump, V delta B. And then state 3, from superheated table, we have pressure and temperature. We have them. Clearly the pressure and temperature superheated. This is, we can get H3 directly from our superheated table, and the entropy at 3. We take the entropy at 3 and we go saturated table at 10 kilopascal and compare S4 that is equal to S3 with SG and SF at saturate at 10 kilopascal. We'll find it is in between, so we can get X4, and then from the equation, H4 equal to HF, which is at 1, plus X4 HFG. If I am going fast, please stop me to ask any question. But I'm talking since we solved it simple Rankine cycle with Dr. Hunter, so table 1 you can get, and you solve it now more complicated problem, which is the regeneration. So you get the properties in the table. So I think you don't have any problem to get the properties of the steam cycle. You need the properties at the main points, 1, 2, 3, 4. And also for the gas cycle, we have a state 5. Either we use the table actually also as isentropic with the variable specific heat, or we can assume constant specific heat. If we assume constant specific heat for the gas turbine, so the efficiency is 1 minus 1 over the pressure ratio to the power K minus 1 over K, which is 1.4, as we did. You remember we solved it together, the gas turbine cycle, either with the constant specific heat or variable specific heat. And we find the efficiency with constant specific heat 38%, with variable specific heat we find it 40%. The book again is giving the solution with variable specific heat, and you can get at state 7 you have 12 Kelvin, so you can get it directly the enthalpy at 7. For 8 it is isentropic expansion, so you can get the enthalpy based on PR to be this 747, and at 6 you have 5, it is 295 Kelvin, so you can get it from ideal gas table directly, 295, and then 6 with the isentropic relation, which you need to get B2 over P1 equal PR2 over PR1, and then find PR2 and go to the table, try to see where is PR2, then you find the temperature and the enthalpy. Is this clear how to get the properties for gas turbine and for steam cycle? Hello? Hello, ya shabab?
Doctor?
Yes.
Steam cycle, it's okay. It's almost okay, but gas turbine, is it the same using the property calculators, or
you can use the property calculator of
with the dry air?
Actually, it is properties for dry air in the calculator, but I am not sure if you can use this variable specific heat to represent somehow the isentropic process using the calculator, the ideal gas calculator, thermodynamic calculator. because you need to do something in between. You have to do, you cannot put the entropy directly there at state 6, because you know the pressure at 6, but you need another property to help you. The other property that will help you is the PR. If your thermodynamic calculator is calculating PR, I mean the one on the internet, calculating PR, so yes, you can use it. But the other option, you have it either the computer aided thermodynamic table from Van Wiley that I provided. I saw some of you solving using it, thermodynamic table. It has PR, because to get the property at 6, you need the temperature PR at 6, PR2, or which is PR at 6. You have PR at 1, you get it from the table, and you take it and go to the table again with PR at 6. But you have also pressure at 6, which is 7 bar in this case. Hello? Yes.
Can you show us an example?
I did that in the last class, you remember, in the gas turbine, we did that. We solved the gas turbine cycle with constant specific heat, with variable specific heat. I can show you now one case in the CAT table, but you have it also in your thermodynamic tables that, let me, someone want to come in. Let me open thermodynamic tables. Either you need the CAT, right? Because this is the quick. I'm not sure about the internet thermodynamic calculator, but here in this we need to use air. Yes, we have it, air temperature in centigrade and pressure in megapascal. So if we start calculating a first example, this is 0.1 megapascal, temperature is 295, so it is 22 degree. Then we calculate the state 5 for the air, and then we have the reduced pressure here is 1.053. So we take it with state 2, we need to calculate state 6. State 6 is 0.7 megapascal, but we have PR, reduced pressure, 1.053. This is what we do, and then we get all properties here. So you get the enthalpy in state 1, 295.6, but enthalpy at state 6, same here. So sorry, here I should multiply this by 7. How much? Let us do this again. This is multiplied by 7. 105, 1.05, 3 times 7. How much? In Excel. 1.05, 3 times 7, because this is the pressure ratio. It's 7.37.
Okay.
So here it is 7.371. Let us calculate that. Now the enthalpy is this one, 550. Then if you want the state 7, which is the pressure is 0.7, but the temperature is 1200 Kelvin, which is about how much? 923, something like this, centigrade. Then calculate, you get the enthalpy like 1273. And then state 4, you have the PR3, 188.7, and you need to divide it by 7. Let me quickly do it. 188.7 divided by 7. I'm not sure I got the number correct or wrong, but this is 26.9. Let us say 27. Yes, it's correct. Let us take it 20. What I did. I lost the Excel. Why I do that? Why I close it? Yes, it is here. It's 27 and the pressure is atmospheric. Let us come to the table again. And this is case 8. This 0.8 and the pressure is 0.1 and the PR is 27 or 26.95. Then we have the last state enthalpy. Is that correct? Let me do it again. Is 0.1 reduced the pressure is 26.95. So it is 201570. Let us see what we have in our presentation, the data we have. Here is 1277. I think this is what we get correct. I did close it. Anyway, I close it. Anyway, you have seen the procedure, how to use the computer aided tables. And I think I explained last time how to use our hard copy thermodynamic tables to get the properties at inlet exit of the compressor and inlet exit of the simple gas turbine. It is 4 states for the gas turbine, 4 states for a steam turbine. And you need to link both of them. Yes, if you have question, please raise it.
PR, is it reduced pressure or relative pressure?
No, it is, they call it reduced pressure because actually it is pressure over or exponent. You got it from the isentropic process. The isentropic process, you remember, it is delta S equal to 0. And for ideal gas, let me write in front of you now, insert in a new, so for ideal gas, or let me use the word, the file. You remember this in the ideal gas for delta S. For delta S of ideal gas, S2, let us say minus S1 equal to S naught at T2 minus also S naught, but at T1 minus R ln P2 over P1. Okay. Now, when I say all this equal to 0, when I say this for isentropic process, I say this equal to 0 here. So I'll find, I can write actually R ln P2 minus P1 equal to, open bracket here. This derivation, I should not do it, but you ask for a lot to understand, and then you complain that we gave a lot of material. But this should be in your background. So you have now this relation for isentropic process, right? we started for the general definition for ideal gas. This is the delta S for ideal gas between inlet and exit. Here we have it 5 and 6 and 7 and 8 for the turbine, 5 and 6 for the compressor. But we are writing just general expression. Now we can have this modified to I can take this R here, come X. I can write it, this, I divide this by that. So R will be here. Then we can write this equation once again in a different form. Then the P2, if you take inverse ln of this, so you will have P2 equal to, here you will find this expression, take this 4. This will be E to this power. And this is what we call it, PR, the reduced pressure, right? So actually, to get this reduced pressure, you need to use the table because you need S0 at T2 minus S0 at T1 over R. And then take this value and put it as the exponent of E. Then you get PR. Actually, the tables are giving that, the hard copy tables are giving this tabulated. So between any 2 points, like P6 over P5 will be E or PR at, actually, if you do this, I don't want to make your life miserable, actually. I will do it this way. This is the correct expression. I'll do it in front of you. Actually, because this is E to the power S0 at T2 minus S0 at T1. So we can separate the exponents. We write it like this, right? We can write it, still write this. We here, and we have here multiplication, right?
Yeah.
Correct.
And then, because this is having minus, so we can rewrite this. Here we can take this, and we take this as the numerator. And we take this here, but now we don't have the minus. So this will be equal to here we'll have PR2 and here we'll have PR1. For temperature 1, you get PR1. For temperature 2, you get PR2. Then you get this ratio equated to P2 over P1.
So this relative pressure is the same reduced pressure.
Actually, this is called relative pressure or reduced pressure, whatever, but you should know why you are using 4, because we do have another PR that is P at any point over P critical. When we see the reduced value or the compressibility factor Z, it is ideal gas or real gas. We have PR in 2 occasions, and we both call it, it's a pressure ratio at the end. It's a pressure ratio at the end, okay? But here you see it is having the effect of temperature into account for the isentropic. And you know from where we derive this. You have this generalized compressibility factor for ideal gas. For ideal gas, we use the equation BV equal to MRT. For real gas, we use a correction. We call BV equal to Z time MRT. This Z, we got it from a chart called generalized compressibility chart. It has PR as one axis, which is actually PR is B over B critical of the substance. It's another story, but let us see the reduced pressure we use here in this isentropic process is this. I got you all the derivation here. But I know you are not interested as your nature, what you are doing in this program. You might not be really interested to do all the detail. You can know it, actually, it is very positive, but you need to focus on the main concept or macroscopic, and this is the purpose of this lecture. Actually, this derivation, I could have give it in your first module, first lecture, but you have seen it was so heavy. Right, but anyway, the information here, you have it. I can upload this to the net, I mean, as this document for your reference. But of course, it is in your also textbook, in a thermodynamic textbook, you will find this derivation. So any further question, please? You know the story of PR from where we used it for isentropic, but this is the case for constant specific heat. Now, if we said for constant specific heat, just to complete this, for constant specific heat, we can have this, yes, because, yes.
Dr. PR means what?
As I said, the pressure ratio, this PR is what you can see from this definition. You can see it here. This is PR. It's not a pressure, right? It is E to the power S naught at T2 over R. We call it PR2. If we take E to S power S naught over at T1, this is over R, this is PR1. But why we call it PR? Because somehow it is related to the pressure ratio, as you can see here. And we use it only for the case of variable specific heat, where we need to use S naught at T2, which is, what is S naught at T2 and S naught at T1? What we get it, you remember the pressure was, here it was Cp, it was integration sign. Let me remind you with some detail you might hate, but you will like to understand it. Let me so it is here, it was something like this. Cp dt from T1 to T2 if I have a process from 1 to 2, isentropic, or any process from 1 to 2, the equation is like this. See, also here integration of R lim P2 over P1, it should be something like this. It should be, but here is R dB from P1 to P2, and Z. Now, if R is constant, we take it out of the integration, then it will be like this. R is here, and this is only dB. right? And if CP is constant, we can take it out as well. Sorry. Right? We can take CP and R out if CP is constant. So what you will have at the end S2 minus S1 will be equal to, this will be now len. What are the functions we have? It is len actually, not log. This one, yes. It will be len. Here T2 over T1 minus also here it will be R len P2 over P1. Now, if this is 0, if this is equal to 0 for isentropic, if I said this is 0 isentropic, then what we'll have? We'll have R len P2 over P1 will equal to Cp len T2 over T1. Then we can say here, sorry, we can take this over here. We can say T2 over T1, or this one, Cp over R. We can take this here. I shouldn't do this in this type of lecture, should I?
We're interested in how to use relative pressure.
Yeah, actually now I can bring this len T2 I can take this one. I like typing equations, but it takes time. And then we'll have this actually will be, I can put this actually in the design, I can put it here into bracket. And then also this one, I can take it here inside. Then all this should be raised to the power what? I can put here this, and it is like this, right? Now I can take inverse len for both. I put them in len expression equal to len expression. So I can take inverse len for both, and then we'll have here just len has gone from both sides, or anyway, and this also T2 over. What is R actually is Cp minus Cv. So if you divide this, it will be, if you divide this Cp by Cv, if you have here this divided by Cv, and this will be 1, and here it will be also Cp over. So anyway, this Cp is, that is not accepting my, yes. So Cp over Cv is K. Cp over Cv is K. This ratio is K. And here is K. So this is what I was telling you. We can, for constant specific here, we can get T2 over T1 equal P2 over P1 K minus 1 over K. This is based on isentropic, and we show you how we get it. And if we use variable specific heat, this is what we get. I think I don't want to visit this again, either this lecture or next lecture. Do you agree on that, that we don't need to visit this again? Just I'll upload this for your reference. Actually, we know that I enjoy thermodynamics. I have passion to it, but not on this level of courses or programs, because this should be in your background. So we have the enthalpies here. What we need to do is to know what is the work per unit mass of the working fluid. Remember, we do have here in the top cycle air, and we have different mass flow rate from the steam here. We have two different fluids. You might have here in the air 100 kilogram per second air, and here we have 200 kilogram per second water. I cannot add them, right? Because even if I have the work here in kilojoule per kilogram, it is per kilogram air, and here I have the work in kilojoule per kilogram, but kilogram of steam. I cannot add them. But if I have here the power kilowatt, which is m dot air delta H for the air, it is kilowatt, and here m dot steam delta H of steam, it is kilowatt. So I can add the kilowatt. But when I add kilojoule per kilogram, I should ask, is it kilogram per air or kilogram per water? Because we have two cycles with two different fluids. If it is kilogram per air, it is different from kilogram per water. Kilojoule per kilogram air is different from kilojoule per kilogram. I need to multiply by the respective mass flow rate. So we need the mass ratio of the air to the water, and this appears in the energy balance. If you remember here, we have in this the heat exchanger, we have air inlet at 8 and exit at 9, and going the fluid coming from, as according to the drawing, from right to left, from high temperature to low temperature, and the water coming from 2 to 3 or flowing from opposite direction, from left to right. So we have it, the temperature 2 is low and temperature 3 is high. As you can see here, the two low temperature are in one side of the heat exchanger for the air at 9 and water at 2. And for high temperature, they are in the other side of the heat exchanger. Air is at 8 and water at 3. This called counterflow heat exchanger. And usually the two hot fluids will be in one side, and also the cold streams will be on the other side. This actually give you idea that the delta T at one side of the heat exchanger always will not be high. So you here in the low temperature side, you have the temperature between T9 for the air and T2 for the water. And here the temperature difference will be T8 for the air and T3 of the water. Still, always the hot stream is higher than the cold stream, or the hot fluid, which is air exhausted from the gas turbine, is higher than the water at inlet and exit of the stream of the water. But delta T in either side of the heat exchanger is relatively low. I can have the inlet of the water at the same side with the inlet of the gas. So you will have the difference in this case between T2 and T8. You see the difference will be high. And this is what we call it parallel flow heat exchanger. Parallel flow, the two inlet of one of the two stream at the same time. Very high temperature from the hot gas and low temperature from the liquid water. The delta T will be very high. This will create actually thermal stresses at the inlet. This is material perspective. And also will have high irreversibility because the heat transfer here happen due to very large temperature difference. When we reverse the flow direction, as we have here in this schematic, we reduce the thermal stresses because the two streams are getting heat gradually. So delta T on one side 8 minus 3 and the other side 9 minus 2. Delta T is not high in either side. So the irreversibility due to heat transfer reduced and also thermal stress reduced. These are the technical things I want to open your eyes to it, because when you are in a plant or in a factory that want to install a heat exchanger, you have option parallel arrangement or counterflow heat exchanger. You should go and understand why you go for the counterflow type of heat exchanger, especially the temperature difference is high. Again, I'm saying these are important. Of course, the detail of thermodynamic are basis of what we are doing here, but now you are in a stage close to decision maker rather than a thermodynamic analysis engineer, right?
Doctor,
If you, yes,
small question.
yeah.
Just from seeing this diagram, we can see that the heat recovery steam generator, that is from state number 9, is actually a small portion of Q added to the steam cycle. So we still need a boiler in addition to the HRSG, or just HRSG is enough?
Actually, here, according to the problem, he's giving that whatever the design of the heat exchanger and the temperature of 8, the source of heating, the boiler or the heat recovery steam generator are enough to do the calculation or to generate the power we want, right? But in some cases, if you need to superheat 3 here to higher temperatures than 8, if you need to superheat more, we add what we call duct firing. We add a burner in the heat recovery steam generation generator. We add a burner and we inject fuel. And actually, we can. If you give me time, I'll finish, and you will enjoy the second lecture more. But let us jump back. This is thermodynamic, but I want to jump into the economics, right? Because this is the focus in our lecture today. But before going to the economic, we need to finish the thermodynamic analysis here. As you remember here, we have 2 inlets to the heat exchanger. We have 2 inlets, one here for the gas, and one inlet for the gas and one inlet for the liquid water. Then we have 2 outlets, one outlet for the exhaust gas and one outlet for the superheated steam, right? So when we make the energy balance, we are saying Q minus W, or heat minus work, equals summation M dot delta H at exit minus summation M dot H at the inlet, right? We don't have in the exchanger Q or W because we insulate, the overall heat exchanger is insulated. So we'll have summation of M dot exit H exit equal to summation of M dot inlet H inlet. What does this summation mean? Means we add M dot gases times H of the gases at the inlet, which is here case 8, and plus M dot inlet for the steam times H inlet of the steam, which is here state 2 for the steam, equal to M dot gas exit, which is here H exit of the gases is 9, plus M dot steam H exit of the steam, which is H3. So when I rearrange the M dot steam, the terms of M dot steam in one side and terms of M dot gas in one side, I'll find that I'll take this M dot exit H inlet, M dot inlet H inlet, or M dot gas H inlet to this side negative, and M dot steam H out will go to the other side in the negative. And then the ratio M dot steam will be delta H for the gas over delta H of the steam, right? So this ratio will give me for each kilogram of gas, how many kilogram of steam. So when I use this in the work here, yes.
Can you please explain the mass balance equation, this one?
I think we did it before, ya Shabab, in last lecture. No. As
for the heat exchanger here in the previous diagram.
Yeah, we did it before. I mean, in whatever energy balance, I just put it in front of you last class. I can get the lecture. said this is the formula we apply to any device. I know today what is going on. I don't know. I don't know, your classes today is happy that they have a lot of delays, huh? Anyway, you see this equation, Q dot minus work dot equal summation M dot exit H exit. The mouse is going everywhere except where I want. I don't know. So when for heat exchanger, the overall heat exchanger that have the two stream of the hot and the cold gas, we insulate from outside. So no heat dissipate to the surrounding. So we have Q0 and we don't have any shaft work or rotating element or boundary displacement. So we have Q minus W equal to 0, right? So the summation mean I have 2 exit and 2 inlet. So each inlet I'll take M dot exit H exit for gas side plus M exit H exit for the liquid side. This is equal to, right? Because this minus will go to the other side, positive, will equal to M inlet H inlet of the hot side plus M inlet H exit for the cold side, or gas and water side. And we get into this equation, right? Do you know from where I got it now? And then you can arrange the gas alone in one side, the steam in one side, and take M dot steam of M dot gas if you to get this ratio. And we have all enthalpies from this table, right? We have delta H, which is 3 and 2 for the heat for the steam, and 8 and 9 for the gas. Okay.
Okay.
Right, because he gave me 9. Now, if I get the work, as I said, for the power, maybe I write it here in this here better. I need if I have work dot total, I need work dot total equal to, it should equal to work dot for the gas turbine plus work dot for the steam turbine. Right? This is clear?
Yes.
Yes.
Right. We need this. We wrote a lot today. So now how to get work dot of the gas turbine? Let me, sorry for this. I should have here M dot gas multiplied by H gas in minus H gas out of the turbine, of the gas turbine. And here I should have M dot steam multiplied by H steam in minus H steam out for what? Of the steam turbine. What are these? H gas in is H steam turbine in is 3. This is H, gas N will be my sink.
Doctor,
7 minus 8. Yes, 1 minute, please.
بس كنت ابغى
And
اسال
this,
Doctor, still solving example 6-8.
yes. I mean, the example actually itself has nothing to do with the thermodynamic because we already calculated the efficiencies before, but this is what you want. You enjoy thermodynamics more than economics, huh? So here you will find you need m dot gas and m dot steam. But if we divide it, what actually the book did, we needed either per kilogram of air because this is the source of the power, or of the heat in the cycle. So we divided by all the equation by m dot gas. Sorry. So you have now the work per unit mass of the air flowing in the gas turbine cycle equal to delta H in kilojoule per kilogram of air in the gas turbine multiply plus here, this is what we just calculated now is what we call a ratio called Y. We'll call this ratio as Y. We got it from where? From the energy balance of the heat exchanger. We got it from the energy balance of the heat exchanger. Right, this ratio Y. We got it from the energy balance here. So from here, you got the overall efficiency, which is the work net, the work of the two turbines, but this Y is the ratio between m dot steam, and this delta H 310 is delta H across the gas turbine in kilojoule per kilogram of the gas, of the air, and 1116 is delta H for the water multiplied by the m dot steam over m dot water. And the Qn, we find it, what is Qn, how to get it? Qn is here, delta H 7 minus 6, delta H 7 minus 6. This is where Qn is for the gas. The ratio give you the efficiency. The efficiency here, you will find it is about, for the steam cycle alone is 38, for the gas turbine alone is 40%, but for the combined cycle is 58. For the combined cycle is 58. This means that when we have these two solutions, gas turbine generation and steam turbine generation, we combine them together, give us a new cycle that has more efficiency. Of course, this means for the same power I get from both turbine, I will reduce the fuel. I will reduce the fuel I am burning if I compare the two. So this is the economic. In case you upgrade a plant, like you have a gas turbine alone, like Goraya power plant started maybe 16 years back with gas turbines only, then they added, but it was built and designed to extend it with a combined cycle to add the heat recovery steam generation at the exhaust of the turbine instead of going to the chimney directly. And even they have bypass. They can bypass the heat recovery steam generation and they can go to the chimney directly, or if they want more load is there, they run the bypass to let the gas go through the heat recovery steam generation. But this actually building a steam cycle beside the existing gas cycle mean more cost. So you have to take a decision either when you build a new plant or even extension like this, adding a steam cycle to the gas turbine cycle, this investment would stay at least 20 years. So we have to take some economic decisions. What are these economic decisions? What are the factors that will affect your decision? Of course, is the capital cost, either to build a new plant, or as I said, you have a gas turbine running and you add to it a steam turbine. What is the initial cost you are paying? And what is the minimum attractive rate of return that you have? Maybe your return in the market, if you put in a business like trading, or you put it in the I don't know, in other business, you get a return of 10%. But if you have your plant, you will have 8 or 9%, and it will be accepted to you or not. This is again economic decision, because as you know, all the power plant in US are owned by people. It's private companies, not by the country like here in Saudi Arabia. But now, as you know, Saudi Electric Company is going to be shared with the public. Also, to run your plant, you use fuel, and the fuel has a price. Now, this fuel cost is the daily or running cost. You have another cost is but when you have the new plant is more efficient, this means you are going to reduce down the cost of fuel. But in front of this, you need to have more manpower and maintenance technicians and engineers to take care of the new plant, or the maintenance and running cost and salaries will be more when you have the combined cycle to compare to the simple gas cycle. These main or three factors, usually you should know ahead what from the efficiency you can get the fuel before and after. Also number of people or employment you can get before and after. Capital cost, of course, when you buy the new installation, but the capital cost will not include only the price of the plant or the devices like the steam turbine, the heat recovery steam generation, the pumps. No, it's also the land and the price of the contractor who will build it. All these are initial, you put it at the front. As you know, the total cost, or what we call levelized energy cost, yani you build a plant to produce electricity, like near Goraya power plant, which is a combined cycle. We have another cycle owned by a consortium or by a company. It's also combined cycle, but they have inlet air cooling, they have the thermal storage, they have a lot of features that make it more efficient than Goraya. Even Goraya is very efficient. But these owners or investors who built the plant, stronger plant, they are going to sell the electricity. How much? Usually electricity is priced per kilowatt hour. This is energy, not power, which is how many you turn on your lamp that use 1 kilowatt or 2 kilowatt for 2 hours, then you consume 2 kilowatt hour. This is what you pay, the price like 25 halala per kilowatt hour or 10 halala per kilowatt hour. This is dependent on your how much you are consuming. So this is what we are calculating. You have made improvement in your power plant. So you produce electricity with what price? If you are going to produce it with 50 halala per kilowatt hour, you cannot sell it in the market because the market price is 25 halala per kilowatt hour. But if you produce it with 5 halala per kilowatt hour from the new plant, then you are making a revenue. You will make a profit, right? So this is how we calculate the levelized energy cost or levelized cost of energy. Some people, they call it LEC, some people will call it LCE. It depends on you put levelized energy cost or you put levelized cost of energy. Anyway, it is in dollar per kilowatt hour or real per kilowatt hour. So it's the annual capital cost. I mean, when you bought the plant with let us say $200 million, and it will stay for 20 years. This means that with simple interest rate or no interest rate, then you will have 200 million over 20 years. So the annual share for each year, as you are put for each year, 200 million over 20 years. So it is $10 million per year. But due to the interest rate, this annual capital cost, we need to put to include how is the annual share compared to the initial cost. Like Dr. Hunter gave you some economic about the present net present value and so on. And there is a formula to calculate the annuity factor or the annual share. If you know the initial cost, how much you can get the annual capital cost or the capital cost from this annual payment, what is the share every year. plus the fuel cost, that is every year how much fuel you bought, plus balance cost, as I said, for engineers, labor, technicians, maintenance, plus ORI. ROI is return of investment. Usually it's a lump sum value, as Dr. Anta said before, but in the levelized cost of energy, actually, we don't use it. We don't put this. This is, if you have this $200 million, how much you expect the rate they bring money to you and put it in some other business, or you put it in the bank with some rate or something. But usually it is, we don't use this part. That's why in the problems you see in the example, he said neglect ROI. Over the energy produced. What is the energy produced? How much power you produce from your plant? Let us say 500 megawatt. This is instantaneous. And the plant is working, for example, in the year 24/7 for a year, continuous with 500 megawatt. So how many hours? So in the year, you have 24 hours per day, times 365 days. It will be 8,760 hours per year, multiplied by the power generated per second, or kilojoule per second, or kilowatt or megawatt, multiplied by the time, it give you the energy consumed, which is here, the unit is kilowatt hour. The unit is kilowatt hour. How many kilowatt time the hours? Usually, as I said, the year is 8,760 hours, but any power plant, it doesn't work in full capacity 24/7 for a year. Usually, sometimes it work at the full capacity, sometimes part load, or like in summer and winter. In summer, all the plants in Saudi Arabia work for capacity. But in winter, it might work at 20% of its capacity. Like I have seen in Guraya power plant in winter, they have 18 gas turbine cycle running 6 steam cycles, right? In winter, they don't run the 18 gas cycle, and they don't run, or sometimes they don't run the steam cycles. So because of the load is less. In this case, we see how many hours of the year. Also, any power plant, it takes 1 month of the year for maintenance, especially in winter, because the load is not much. So they can turn off some plant for major maintenance. So let us say each plant work for 80% of the year with full capacity, or 70% or 50%. It depends on the scheduling of your power plant. So this is also how to calculate the annual kilowatt hour. It is the power rated capacity times the capacity factor, how much percent of the time, time 8,760, which is the hours of the year. This is energy out. How to calculate energy in? We divide energy out over overall efficiency. What is the overall efficiency? It is efficiency of the cycle, which is eta thermal, either of gas turbine alone or steam alone, but in combined cycle, it is the efficiency of the cycle multiplied by the efficiency in the combustion system. Sometimes, as we know, the combustion system itself is very vital, because you have 1 kilogram of fuel, you burn it. Did you burn it all, or you have some liquid fuel go out without burning? So the combustion system has efficiency. Also, do you have a full insulation, so that all the fuel come from the energy come from the combustion, went to the working fluid, or some has been gone, like in the boiler on the heat recovery steam generator, the body of the burner is hot, so there is radiation loss to the surrounding. This also reduce the efficiency of the combustion system. Also, your electric generator, you have mechanical energy come to the electric generator, and out of is electric energy. But inside the electric generator, there is the friction in the bearing. There is also electromagnetic losses in the coil of the generator, so it doesn't have 100% efficiency. So when you talk about the plant, you have electricity at the transformer or at the bus bar of the power plant, and you have a fuel at the input. The ratio of the energy of this electricity to the chemical energy in the fuel should include the combustion efficiency, the cycle, thermodynamic cycle efficiency, and the electric generator efficiency. You multiply the three, this gives me the ratio between the net electric power at the bus bar of the plant and the chemical power or energy in the fuel. So this, how to calculate energy out, as I said, capacity factor, time capacity of the plant, how many megawatt, time hours of year, we said 8,000. But here, this will give us in kilowatt hour or megawatt hour, but we need to convert it to joule. So we multiply each megawatt hour equal to 3.6 gigajoule. This unit conversion, I can talk to you how we get it, but it is simple. 1 kilowatt hour mean 1 kilojoule per second multiplied by 3,600 seconds in kilojoule. It will be 3,000 megajoule per kilowatt hour, or 3.6 gigajoule per megawatt hour. So now this energy in is the fuel, actually the energy in the fuel. It is energy out. We calculate it from this equation divided by the eta overall, which I said eta combustion, eta thermodynamic, time eta electric generator. Now this is an example that is asking us to carry out a financial analysis of a coal-fired plant that you solve it with Dr. Hunter in example 6.1. It's a simple Rankine cycle, right? Excuse me. Then the actual cycle that, or the ideal that has isentropic bumping and isentropic expansion in the turbine gave us, let us say, efficiency 25%, but he said due to actual reversibility, efficiency of the plant is only 80% of the ideal one. Now he's saying, so whatever we solve it in example 6.1, efficiency was 25, we need to multiply it by 0.8. Is this clear? Is this point clear? We are not going to calculate the efficiency now. We just to go to example 6.1, find the efficiency there, multiplied by 80% here, then this is the efficiency of our plant in this example. Clear?
Clear.
Now, the efficiency of the boiler, I mean the combustion here, efficiency in the boiler is 85. This is eta combustion. And of eta generator is 98. So we can multiply this 85 times 98 times the efficiency of the plant, which is 80 times the efficiency in example 1, and get the overall efficiency. The plant is rated as 500 megawatt. This is simple Rankine cycle, 500 megawatt, and has capacity factor of 70%. You remember here, this is the equation we are using to get output power. Capacity factor 0.7, capacity is 500 megawatt, number of hours in year, it's 8,760. To convert, we have all this number, 0.7 times 500 megawatt times 8,760. This gives you in megawatt hour, multiplied by 3.6 gigajoule per megawatt hour. So whatever the number, it will be in gigajoule. And we divide this by eta overall, it will give us the energy in, right? He said that this is actually how to get the, sorry, let us go back to the problem. This is how to get energy out and energy in gigajoule. Now he said the initial cost of this simple plant is 200 million. So we need to get what is the annuity value or the annual share. The plant will work for 20 years and the minimum attractive return rate is 8%. The balance cost, which is the second component, is 18 million per year. This is one piece. From table 5.2, you can get how much the cost of the 1 ton of coal in chapter 5. We give tables, range, depend on the type of the fuel. And also this 1 ton and energy content is 25 gigajoule per ton of that coal. So if we know how much a gigajoule we'll need at the input, we divide it by the energy content, which is 25 gigajoule per ton. So we know how many tons we need of coal. So we multiply this how many tons by the price of 1 ton. This gives us the fuel price. This gives us a fuel price over a year. So let us go step by step and see this, all the information he gave to us. Now we are going to solve step by step. If we miss one information, we'll go back to the question and read, find out what is this. So he needs to solve us to get the levelized cost of 1 kilowatt hour from this plant. The second, he said, if we have this plant, we modify it by using super material, super alloy in the system, in the turbine, in the piping. Then we can raise the pressure of the steam and temperature to be in the super critical region. This means you buy expensive material of your component. You have very expensive material for the boiler, because it's high pressure, high temperature, high expensive material for the piping, high expensive material for the turbine and for the rest of the cycle, the pump, the piping, and other things. This costs you $100 million more. So the new plant has 300 million, but the efficiency is higher. So it will save more fuel. This will give you more attractive price for electricity. It gives you more profit. Let us see. We'll solve the two, get the levelized cost of two, and see which one is better to us. Now, this slide is repeated. Now for case one, the overall efficiency, as we said, the first efficiency was 0.253 multiplied by 0.8, because he said 80%. From solution of example 6.1, the efficiency was 25.3 multiplied by 0.8 to take irreversibility into account, then it is 20. So this is eta thermal of the Rankine cycle. It's a simple plant. This eta generator, 98%, and eta combustion, 85%. So the overall efficiency is 60.9. And capacity factor is 0.7. Capacity of the plant, 500 megawatt. Number of hours per year, 8,760 hours. Multiplied to convert this in I don't know, we multiply by 1,000. This is megawatt hour. Yeah, we got it here in kilowatt hour. We multiply by 1,000 to convert it to kilowatt hour, but we need it actually in gigajoule. So we should leave it in gigajoule directly, like here. Multiply by 3.6 gigajoule per megawatt hour. This conversion factor, you can drive it even. So the output power is 11 times 10 to the power 6 gigajoule per year. Now, the fuel cost, I need to know the input fuel energy. So I divide energy out over overall efficiency of my plant. That consists of what? Combustion system in the boiler, the thermal efficiency of the cycle, and the electric generator. So the input overall efficiency is 0.169. So the input energy to produce 10 to the power 6 gigajoule, we need 65.5 10 to the power 6 gigajoule input. But I need this from burning coal. He said each ton of coal produced 25 gigajoules. So I divide 65. I use this in Excel here. I divide this here, as you can see, the 65.5 gigajoule divided by 25, it gives us 2.62 million ton. And now we have this 2.6 million ton. Each ton costs $35. I calculated, I multiplied, it gave me $91.7 million per year. This is the price of the fuel. This is the price of the fuel. Now, I got the price of the fuel, 91.6. He gave the balance cost for labor and the engineer as 18 million, but he gave the price, the initial price of the plant as 200 million. But I need in the equation per year, how much per year will contribute this initial cost. So this is the equation, how to get A over B depending on the interest rate, which is I, and N is the number of years. If you calculated this ratio or the annual annual share of this 200 million, you can get. Actually, there are some statistical software you can get, or tables. You get the interest rate, the number of years, it gives you the ratio A over B. So here we use the expression and substitute thermal simple algebraic calculation. I put here the equation and I put here the expression based on this equation from Excel. I got it. Maybe you have it in your function, in your calculator. Maybe you have the table or you have a software to do it. Okay. Then what happened? I got the annuity factor multiplied by now the annual capital cost plus fuel cost plus balance cost plus return of investment, we consider it 0. So the annual share we got here 0.102 multiplied by 200, this is 20.4 million, and the fuel cost is here 91, and the balance cost, as I said, salaries and wages is 18. Over how much energy produced per year? This is the 3.07 kilowatt hour. This is the levelized energy cost. Okay. Now he said in case 2 that you have another supercritical plant that is more costly. The efficiency here, if you notice, is higher. It's 39. The other one was 25. We'll do the same analysis. We multiply by 80%, then the efficiency of the real cycle with irreversibility is 26. The annuity factor is again 0.102, but the initial cost is 300. So this the annual share here from the initial cost is 30. The fuel cost is less because the efficiency or overall efficiency now is less, but the balance cost is the same, labor and engineer, over the same power output, which is 0.0. Now the levelized cost is 0.0353 per kilowatt hour. You remember the other one, the levelized cost was 0.04 and here 0.03. So if you are selling your electricity at $0.1 per kilowatt hour, so you gain about 65 cents per kilowatt hour, but here your gain will be 60 cents per kilowatt hour. So this will give you more profit. But again, as a designer or as an owner of the plant, you have to make the decision at the end. Nobody will force you to make the decision. Actually, for the sake of the schedule of our class, I want to just give a small lecture, maybe 10 or 14 slides about the environment impact. Would you allow me to go for a few minutes here and then close the session?
But Doctor, we are very tired.
I know, but this material, can you read it and we have a quick discussion on it next session?
Sure.
Doctor,
Right.
our next meeting will be on Tuesday, right? At 8 p.m.
Office hour?
No, we agreed last week that you will give us extended help session at Tuesday.
Yeah, no problem. But can we go quickly through this because it's descriptive. We don't have much.
Yeah,
analysis.
I was just asking about the next meeting.
Yeah, I agree to give you any time. You can communicate with me through email or with Dr. Hunter, but I have no problem. I know you have it at 6 p.m., but if you need it at 8, it's okay.
Okay, thank you.
All of you agree?
We will agree on the timing and I'll send you. I'll discuss.
Do you have a WhatsApp group?
We have a WhatsApp group.
Do you have my phone number? You can add me or.
Okay, no problem.
Or you don't want me to be in the group?
No, بالعكس يا دكتور نتشرف.
Okay, my phone is 056.
Okay, just a second. 056
9847
9847
565.
565.
Okay. I wanted to discuss something with you also first. Actually, we have 3 different, I don't know what this line is. Come in my screen, this green line, I don't know from where it came. We have this thermodynamic part about power cycle, gas power cycle. Then we have the economics and environment. Then we have the carbon sequestration or تخزين الكربون. So I prepared the homework from your book, actually. Even I got the problem from your book, the number of it. I found that 4 problems cover all what we did. Like a first simple gas turbine cycle. Second is to calculate from this simple gas turbine cycle how much CO2 is emission and other thing. Then I made a combined cycle to get its efficiency. And then economic problem, like the one we were solving now. I think, is it fair enough or good idea to release this homework to you to start working on it then I add to it after next session, next Saturday, I have one problem on carbon sequestration or so, or two, then I add it. So you can utilize the time from now to start working on the homework.
Yes, please.
Okay, I can do that. Okay. But we
دكتور
are going to add one more problem or two to it. Yes. Yes.
دكتور ممكن تخليه على السيشن القادمة، يعني تعطينا اياه على السيشن
It
القادمة.
doesn't make difference. I'll put it. Who is interested to solve, he can go and solve. Who has a question he can raise in the office hour. And who doesn't have time, he can start. I mean, the due date is the issue now. Due date will be fixed for all as we agree. But the disclosing it, I can disclose it even from the beginning of the semester, isn't it? But the due date when you should submit is what should concern you.
Yes.
Right? And I'm just seeking an idea with you. I'm not forcing anything.
Yeah, true. What matters is the due date. If you post it now, we can practice.
Yeah, you can start at least see where I am focusing. What are you are lacking to understand or to ask more, right?
Good idea.
Now I need just 10 minutes to finish this lecture. Should we? And if we didn't cover anything, we can visit it again. But at least I want to give what is the theme of the lecture, why we are, what we are discussing. Can I go for 10 more minutes? Yeah, Shabab, I know you are tired, but yeah, anyway, I'll give you a زبدة زي ما يقولوا يعني.
عندنا بالسعودية يا دكتور يقولوا انت ابوها وسمها. انت ابوها وسمها.
يعني انا اعمل اللي انا عايزه يعني؟
بالضبط هذا زي كذا.
ايه دكتور لو تبينا نجلس لين 8 PM.
لان انا صبرت معاكم في الامتحان واديتكم ربع ساعه، خدت وصلت ساعه الا ربع زياده يعني.
يلا يعطيك العافيه. Go ahead please.
طيب احنا environmental consideration now are very important because of the global warming, and I said one of the vital substance we are producing is the CO2 or carbon dioxide that contribute a lot to the global warming. And that's why most of the world countries are trying to put some constraint on the emission of CO2 from any industry or from any activity. So actually CO2 is coming from burning fossil fuels. That's why they put laws on. It's important for us when we talk about energy conversion, because we are burning hydrocarbon fuels that produce always CO2. So if the plants now want to put regulation or to comply with this regulation, they need to put emission control, especially some fuels that have sulfur or NOx, or the combustion at high temperature produce NOx or nitrogen oxides. So sulfur and NOx are producing harmful gases to health. So there is a strict regulation on it. That's why Aramco spend a lot of money to clean the oil and gas before export from the sulfur, because the nature in the ground has sulfur. So the Aramco pay a lot of money to clean the gas and the oil before the export, right? And this of course make difference in the price. But anyway, what I want to say that when you put regulation on to control the emission, you need to add some device to your plant, so it will increase the cost. So you need to take this into account. Now most countries, as I said, they put restriction or legalization on the sulfur and NOx emission, even from the car. That's why you need to make your car istimara. You need to go for gas emission, and this is vital. They have to adjust whatever combustion system to reduce these gas emission. CO2 is not harmful, as I said, to the health, because naturally exists in the earth. But some countries want to make the people reduce because of the global warming. So they give they put some countries, not all countries, like Sweden. They said if you have a power plant or any industry or any activity that produce CO2, you have to give a taxes of $150 per ton of carbon you emit to the surrounding, to the environment. But if you have an important industry and you operate many or employ many people, then they give you discount 75%, or you pay only 25% of this 150. This is just to attract the people, but also if a country like Sweden puts such a tax, they will use the input of the tax from money come from the people they pay the tax or carbon tax. They use it to help the people or researcher to innovate new ideas for carbon capture or for reducing or controlling the pollution. And also they might help other developing country, like in Egypt, for example, if they want to apply this control. Actually, it's important to know each fuel, because some people, they burn a natural gas, some people, they burn coal, like in China and Russia and US. They have a lot of resources of coal, so they burn coal, which is very difficult to burn and produce a lot of CO2 because it's mainly carbon. But here we burn natural gas, which is CH4, it's mainly hydrogen, and exhaust oil from CO2. When you burn natural gas is less than when you burn coal. And also we have the benzene or naphtha or whatever, it's a hydrocarbon, it's a mix of carbon and hydrogen. So each fuel produces different amount of CO2 per kilogram of the fuel or per ton of that fuel. In chapter 5, you have some tables for that, but also I tried to bring some internet links that help you to see for each fuel how much tonnage you are producing. This is example for wood, beet, lignite, oil fuel, crude oil, how much kilogram of CO2 per kilowatt hour or per kilogram of CO2 per gigajoule you produce. This is also from the website. Here's that example. Now we can solve the example next time. But what I want to say, when you introduce some technology like what we call here, I'll solve the example next class because you are tired, but quickly I want to tell you, now we have a plant that want to build a gas turbine. Gas turbine, better or the best to give it gaseous fuel. So what they are doing now, if you have a source, big source of coal, like in US or China, they convert it now with some technology called the gasification. So mix steam with the coal, they burn it partially, then they convert it into synthesized gas with the help of steam and CO2, which even recycle. This is a way to recycle CO2. Then you convert to hydrogen, and then you use fuel cells, which give you electricity very clean, with the output is what, H2O. But now the technology here add cost to you. Now Aramco also is asking, I am working with them in a project to convert the heavy oil into hydrogen. So instead of exporting oil with heavy oil with low price, they can export hydrogen now. And this play two rules. First of all, you increase the income by having add value by fabrication to the oil, like making it plastic or making it hydrogen. Also, you are contributing to the environment. Some other ways, if you have the coal, this is what one of the plants that I give as a senior project to my students, they have what we call carbon capture. Carbon capture is you need to take the CO2, separate it from the exhaust gas and pump it to the ground in some old reservoir that has no oil anymore, so you can pump CO2 in it. So this is sort of a combined cycle where we have here a gas turbine cycle, and here we have a steam cycle. So instead of taking air, and the air, when you burn it with even natural gas or oil, you will produce CO2 plus water plus nitrogen. To separate water, you can condensate, you can cool the gases, and then the water will condensate and separate. But how you separate the CO2 from nitrogen? Someone will say, why we separate it? We bump nitrogen down in the reservoir. Oh, Nitrogen is the major part, I mean, as a gas contribution in the exhaust, and you pay a lot of pumping power to put unharmful gas into the ground. Why? The compression cost will be high. So better to separate nitrogen either from the beginning, we call it pre-combustion or oxy-combustion. You bring a unit that separates the oxygen from the air and take the nitrogen, bump it back to the atmosphere, or take it for fertilizer industry, or take it for hospital. Like we have factories to produce oxygen bottles and nitrogen bottles. Actually, Air Product is building a mega project in Gazan to separate the oxygen from air, and because there is a petrochemical industry there, so they use nitrogen maybe for petrochemical or for fertilizer, and the oxygen for to convert, I mean, to have power plant like this. So separating the oxygen from air, it has different technology. One of it is the cryogenic, or to cool the air and compress it to liquid. Then you leave it to heat up. The nitrogen will boil at different temperature from oxygen. You can separate it. This is the separation, but it needs energy. Anyway, you take the oxygen, burn it in the gas turbine, and then take the exhaust, which is now CO2 plus H2O, because you take the nitrogen out, cool the exhaust gas in a steam cycle, and cool it more by some water. Then you have the condensate, the water. You can take it back, the water, actually they injected in the turbine to cool the turbine, but you can take fresh water. And then the CO2, now you have CO2, which is considerable volume. You can compress it by a series of compressors, then put it for sequestration. I give this project actually to a group of senior project to compare with. If you have another technique that you have, this is a gas turbine, this is the heat recovery steam generation. You burn air as usual in the, sorry, this is the steam turbine. The gas turbine here is the red one. You burn a normal air, and then you have exhaust gases here with CO2, nitrogen, and H2O. You take it for what this is called post combustion. After the combustion, you separate the CO2. They put it for chemical looping. They have the exhaust gas that, as I said, have H2O plus CO2 plus N2. They circulate it in a liquid here that absorb CO2 at low temperature, and nitrogen will be free. Then they can pump it out. Then they take the solution that have CO2, solve it in it, dissolve it in it, they heat it back, then the CO2 will separate, and they take CO2 for sequestration here at this point. And the liquid CO2, the liquid that absorbs CO2, they pump it back to the first column. Then this this separation process continue. We call it chemical looping. If you are interested to have a project on studying one of these carbon capture power plant that produce power, and also you can capture CO2, you are welcome. Either oxy combustion, the first one, or this one, or you study both. Actually, we have a software called ThermoFlow, and we are updating the license, but we have limited seats, only 2 seats. I don't know they updated or not, the university. That give us all the economics, including the price of each device here, the thermal properties of every device, even the cost of the land. If you want to change this gas turbine from GE, different brand, frame 7, or from different frames, or you want to have from ABB or from Mitsubishi, a lot of economic thing is there. You don't need to write a code yourself, but you need to know how to make. This example is there in Thermoflex. You can take it and modify it. For example, the inlet condition of the air in Saudi is different than US. If you want to change the chemical looping, then you can have this cycle or this cycle. Anyway, the software itself is very powerful. We don't need to worry about any economics. It is already there. And then that's it for today. We are left only for economic example on CO2 emission or taxes, and we'll continue next time, inshallah.
Doctor.
Yes.
So now we covered in this session and last session all chapter 6 from the book.
Yeah, actually, Dr. Antar started with the part from chapter 6 last time. He gave the revision and economic, I think, from chapter 1 to 3. Then he jumped to chapter 6 for Rankine cycle. Then I continued from there. Next class, I will solve this example and go to chapter 7. But chapter 5 is linked to us from information point of view, like how much CO2 emission from different fluids, how much is the energy when you burn different fluid. Just a few tables or 2 tables we need to look at in chapter 5.
Doctor, small question.
Yeah, please.
Regarding the CO2 emission from different fuels that we have in the slide, from what I understand that the same unit could give out different emissions depending on the load and premix of fuel. So this
Yeah,
takes into
actually,
account.
combustion. Actually, what we have here is not exact numbers, other than approximate, because it depends on the efficiency of the cycle. Because how much, if you have your combustion system is bad, is not getting full energy from the fuel, so this number will change. Sometimes they write it range, right?
It's sufficient for the research and our purposes.
Yeah, actually, for research, you need to get more accurate information, but I don't know. I don't know how you get accurate, because always there is uncertainty, especially when we come to the research. You don't have the unit yet up and running. But of course, all plants, especially the power plants, when they have boiler or gas turbine, they do have a combustion analysis, sophisticated combustion analysis. And from the combustion analysis, you can know what is the efficiency of combustion. And of course, don't forget that always when you have exhaust gas out to the environment, you need to have the exhaust gas either coming from a boiler or gas turbine. You need to have temperature not less than 130 degree. Why? Because I said most of the fuel have sulfur, and when we burn it, we have sulfur oxide or sulfur trioxide or dioxide, and you have water also, water vapor coming because you burn hydrocarbon.
Okay,
when
so its
the
unit
exhaust
is
gas, when you have the exhaust gas, you try to take all the heat into your cycle, it will cool down, and maybe some water vapor will condensate. When it condensates in the presence of sulfur oxide or sulfur dioxide, it dissolves in this liquid water and produce sulfuric acid. And sulfuric acid eat the material, like if the chimney is from steel or even coated with some thermal bricks, then it will be eaten, and the lifetime of the chimney will deteriorate very fast. So always, if you have the exhaust gas go out of your system at 130 degrees, this is a losses, and it is now counted in the combustion losses or the power, or that's reduce the efficiency. Even you have the combustion is very efficient, everything is nice, you don't have heat loss, but you are exhausting gas at high temperature from the boiler. I'm not talking now about even for the gas turbine. Of course, it is clear that we have exit at high temperature, but even if we have in the combined cycle, still we took some heat to the water to boil the water for the steam cycle, but still exhaust, as you see in the example, the exhaust from the heat exchanger for gas 400 Kelvin. 400 Kelvin mean 127 degrees Celsius. It is lost.
Makes sense. Another small question is there a regulatory body that checks this emission from power plants and do penalize people, or just we do it just for the sake of environment? There is no actually regulation and or penalty.
Actually, I think there is now regulations. I think in industrial city, there is Medina, or I don't know what they call, Gas and Medina is checking now even the pollution in the water, maybe in the exhaust, but in the power plant, they check for themselves because of the efficiency of the plant. This is regulation internal by SEC, Saudi Electric Company. But I mean the city regulation, like in US or in Europe, they have this body who check. But in Saudi Arabia, the check is still internal. Okay,
Okay, thank
but
you.
I don't know if they apply regulation. Of course, with time it will be forced to all. But what I am sure about it is the quality of water, is the sewage water coming from the factory. I'm sure they put some regulation. You cannot send any chemicals with any percentage to the sewage line. You see this industrial lake in Medina Sanaiya, Tanya. There is industrial lake.
Yes. Yes.
Actually, there is a control on the pollution in the water. I'm sure they are applying that. But is it also in the emission? I'm not quite sure. The values are there to apply the law, but to force it is something different.
Okay, makes sense. Thank you.
Yeah, you are welcome. Any other question? Any other question, ya shabab? I'm sorry to squeeze you, but we need actually, I wanted you to go out from the panic of thermodynamic equation, especially after the exam. But you pulled me to typing the equation and find the origin of some expressions. It is helpful to you to understand from where it comes, but I don't want your mind to go for many details. But I want you to, especially in this lecture, I wanted you to think strategically rather than thermodynamic. Of course, thermodynamic detail when you come to complete analysis, or you are a owner of a company or a manager in a company, you have your people who will do the analysis and help you in doing it. Of course, you should, as top manager, you should be able to know what they are doing, how they are doing it. But also you have to think overall to guide all of them. So this is the transition between last time lecture and today lecture. Any other question? Hello?
يعطيك العافية يا دكتور.
خلاص, I will end the session. And thank you very much for your attendance and your patience. Again, I will post the lectures. I have little minor editing in it, like a repeated page as you have seen. I will update the version with any corrections. But if you find something, let me know. Also, I'll put the homework just for your reference. If you have any questions in between, let me know. Also, you need to let me know when you need the office hour. Okay. And that's it for today. Have a nice week, inshallah.
Thank you so much, Dr. يعطيك العافية.
Thank you so much.
السلام عليكم ورحمة الله.
خلص الويكند يا دكتور خلاص.
والله عندك حق يا أخي. أنا قلت have a nice week. أنا قلت have a nice week ما كملتش end. أخدت بالي إن الويك إند خلصت فأنا قلت have a nice week. بس أنت خلاص أنت حطيت نفسك إنك أنت ما عندكش week end.
Yeah, that's a very good use of the weekend. Thank you.
Yeah, inshallah تكون for your benefit and for the country benefit inshallah.
إن شاء الله.
إن شاء الله الله يعطيك العافية دكتور.